Thank you very much, Ian and Lucinda and your teams. It really is a privilege to be here and to be able to talk about two topics that I have been working on for a long time is genuinely a privilege, and I really appreciate the invite. And Lucinda keeps joking about me hanging out to get out of South Australia, but it actually is quite nice at home. But and I don't enjoy plane travel, but I definitely enjoy coming to days like today. So what Ian asked me to speak about was the science about Black Baldies. So I'm going to sort of take you through some of that, and where I'm going to end up is talking about genomics and how we can use genomics to be able to pull apart some of the things that we never used to be able to do before. So Steve gave a great introduction to genomics and sort of the extent of the information that we have with genomics last night. And so I won't talk too much about how it actually works, just the power of the information that we can actually get out of that. And I'm hoping that I'll finish in reasonable time to be able to have some questions. One of the things that I worked on actually in my honours degree and in my PhD was some formal crossbreeding type trials. And I actually started off working with sheep. But one of the formal trial, the way that you would design a trial to be able to get information where you can understand the different genetic effects that are occurring is what we refer to as a diallele cross. And that's a cross where you have all the different combinations. So you've got however many breeds you have, and you could have 12 breeds if you wanted to, but in a really simple, the most simple diallele cross, you've got two breeds, and so you've got both dam breeds, and in this example where we're talking about Black Baldies, you'd have Angus and Hereford dams, and you'd have Angus and Hereford sires. And so if you've got two dam breeds and two sire breeds, there's four possible combinations that can come out of that. You can have Angus by Angus, you can have Hereford by Hereford, and then you can have Angus by Hereford and Hereford by Angus. And so what you have in those crossbreds, so they're the ones on the diagonal in purple, both of those would be Black Baldies. So both of those are half Angus and half Hereford. They're both Black Baldies, so they're genetically the same, but actually one of them has an Angus mum and one has a Hereford mum. And so by being able to have all the crosses there, by being able to have all the crosses there, you're able to separate out the fact that there could be a maternal effect. And so but the difference between those two reciprocal crosses is that maternal effect. The difference between the average of the crossbreds, you see the average of the purple ones in this graph, the average of the crossbreds and the average of the purebreds, that's the heterosis effect. So it's not, the heterosis is not one crossbred compared to one purebred, it's the average of the crossbred compared to the average of the purebreds that went into that. So, Brian, I'm not sure whether you're flabbergasted or hitting a mozzie, but I just saw you go like that. So the trials in the early days were well designed because the only way they could get a handle on the different genetic effects was to have all of these different crosses. In later times, most of the trials that have actually compared, say, Black Baldies with purebred Angus, and let's be frank, a lot of the reason for doing that is that a lot of the herds in temperate Australia and the US have become Angus dominated, and so Hereford are looking for opportunities to be able to sell bulls into Angus herds and demonstrate the benefit of it. So in those examples, and the Black Baldy trial that we ran was just had Angus dams and Hereford bulls crossed to it, and so it's only those ones that are circled there that were actually included in the trial. So that's really great from a commercial point of view to be able to compare Black Baldies to purebred Angus, but it's a slight disaster from a genetics point of view in terms of being able to separate out the different genetic effects. Can you see the issues that would be there? So just to say the same thing in another way, I've got a table here that shows in the different crosses, so the top two are the purebreds, red for Hereford and black for Angus. That's not that creative, is it? Black Baldies we could think they're pretty special, so they're at a purple patch, so they're in purple. So what percentage of Angus genes are in a purebred Angus? Well, 100%. What percentage of Hereford genes are in a pure Hereford? 100%. In a Black Baldy, there's 50% of each. So that's what those first two columns show. And then we've got the maternal effect. So an Angus has an Angus mum. A Black Baldy that has could have an Angus mum or a Hereford mum. So they're the different maternal effects there. And then the question is, do they have heterosis or not? And the purebreds don't have heterosis, we say in general, and the crossbreds do have heterosis. Now, heterosis is the same as hybrid vigour. Hybrid vigour is the common name that, we observe that crossbred animals tend to be more vigorous. I remember my father-in-law, when I was doing some of the early work 30 years ago, and I said, well, how do you describe crossbreds? He said, well, they're just better doers. They get on the ground and get up and running faster, and they're fitter and all that sort of thing. That's hybrid vigour. The flip side of hybrid vigour, and it literally is the alternative thing, is inbreeding depression. So we have variation in how inbred purebreds are, and that's not, we don't really talk about having variation within purebreds in how much heterosis they have, but in reality, some animals have a lot more genetic diversity in them than others. And immaculate conceptions happen, and sometimes sons get over their mums, and all that sort of thing occurs. And when you've got the genomics, you can see that there's actually less diversity in those animals because they're actually inbred. And so what we're doing in crossbreed, when you're forming a breed, you actually are inbreeding to some extent to fix genes that make animals look like that breed, like black coat colour or polled or white face or red coat colour. All those sort of things have been fixed so that all the animals breed true to type. That means they're partially inbred. So what you're doing when you're crossbreeding is just reversing that inbreeding effect. So that it's not something new. Heterosis is the fancy word for it, although we've got an even fancier word now in genomics called heterozygosity. It's actually pretty hard to go past the really early work that was done by the United States Department of Agriculture in Nebraska. And there's a couple of papers that report this, but I'm actually going to go through this carefully, and I'm conscious that at the back the numbers, especially on the TV, don't show up that large. And I think best not so much to look at the actual numbers but the percentage differences, because all of these breeds, you would well be aware that they're quite a bit bigger now and grow quite a bit faster, and we've made a lot of genetic progress in the breeds, so they're not the same as what they were. But if you think about some of the traits, now the number that conceived at first service, the heterosis effect, now this is not Black Baldy compared to Angus, this is the average of the crossbreds compared to the average of the purebreds. Now, it is possible that one of the purebreds is actually better than the Black Baldy, but this is the average. It's an average of the crossbreds compared to average of the purebreds when they've held all the different animals in the cross. So those that conceived at first service, heterosis gives you an extra 6.6%. Pregnancy tested in calf, an extra 5.2%. Live calves born. Now, the effect in their trial was small in heifers. In cows, it was a fairly big effect. I think in some of our stuff it might be the other way around, but that was what they found. Live calves weaned, 6.4% advantage of the crossbreds over the purebreds. Birth weight, an increase in birth weight. Now, if an animal's going to grow faster at one stage, they're likely to be bigger at all stages, so you actually get a bit extra birth weight, 1.6%. 4.3% at weaning, milk production at 6 weeks, 7.5%, so that's the effect of having a crossbred mum. Weaning weight weight of calf weaned per cow join, on this one 14%. I'll show you some other figures on that in a moment. And marbling, 0. We don't actually expect heterosis for marbling, or even carcass composition traits, like if you looked at lean meat yield or meat to bone ratio or some of those types of carcass composition traits, we don't get much heterosis. We tend to get heterosis more for survival type traits or fitness type traits that have lower heritabilities, so that the traits with high heritabilities, we can improve those from selection. The traits with low heritabilities, crossbreeding traditionally has been a way to be able to utilise that. Ian?
One just quick question.
Yeah, just before I start answering questions, what time am I finishing? Till 9:15? Okay, thanks. So this is averaged across both. The difference between them, 30 years ago, as I was working on this stuff, we just assumed it was due to milk supply. And certainly at that time, Angus had the reputation of having a higher milk supply than Herefords. That's a mixed blessing depending on the environment. So you would expect that you would get more heterosis expression in the Black Baldy with the Angus mum than the one with the Hereford mum because of more milk supply. We now understand epigenetics more in that sometimes genes that have been passed from one of the particular sexes get expressed more if they've come from, say, a dad versus if they've come from mum. And in a Brahman Hereford cross, for example, if you look at birth weights, I don't know how many of you have crossed cattle to Brahmins, but if you look at the birth weight of a Brahman Hereford cross, if it's a Hereford bull over a Brahman mum, it'll be quite a low birth weight. If it's a Brahman bull over a Hereford mum, and the same goes for Angus, like any Bos Taurus, if it's a Brahman bull over a Hereford mum, you can end up with some really, really big calves. And we now know that's actually an epigenetic effect. It's obviously nothing to do with milk supply. It's actually the non-genetic effects, or it's just the genetics being expressed based on which sex they were inherited from. Now, those traits, it's hard to show in normal breeding programs how they have a big impact, but we do know in Brahman crosses, certainly for a trait like birth weight, it can have a huge impact. So have people observed that before? If they've ever had Brahman bulls come over their Bos Taurus cows and they can end up some huge calves? Yeah, okay. There's some pain associated with that experience, I assume. So that's an epigenetic effect. But so, you're right, Ian, this is the right data. This is lock these things in because this is designed properly. It's old data, but I suspect that the percentages hold up well. Now, this is a graph that I've been using in my teaching for a very, very long time. I don't think I have any former students here today, but if I did, they would say, I remember this graph. And it's actually a really, really important one, I think. So this is, in that trial, they actually had a 3-breed diallele. So it wasn't just Hereford and Angus, but there were other breeds there. It might have even been more. They had, if it was a 3-breed diallele, there's 9 breed combinations, and they had all 9 breeds. And so you're comparing the average of all of the crossbred. So in the 9 breed combinations, there would be 6 crossbred combinations and 3 purebreds, if there was a three breeds to start with. So the data that you would see here is the average of those 6 crossbred combinations compared to the 3 purebred combinations. So genuinely across the different breed, taking out the breed effects and saying across the breed effects, what's the actual heterosis effect? And then the trait that they're looking at here is weight of calf weaned per cow joined. And it's compared to the base level, which is the purebred performance. So what it's actually addressing here is how much extra performance can we get by either a calf being crossbred or having a crossbred mum. Now, the effect of being a crossbred yourself, we call that individual heterosis. That's the effect of the individual being crossbred, of having the heterosis in itself. The effect of having a crossbred mum, we call that maternal heterosis. So hopefully what you can see here is that the effect of being crossbred yourself increases weight of calf weaned per cow joined by 8%. And then the effect of having a crossbred mum, so this is through slightly higher pregnancy rate, higher calf survival rate, higher growth rate, higher milk supply from the mum. So it's the combination of all those different things. That adds another 15%. And so the effect, the heterosis effect, if you compared, and this is with 3-way crosses now, compared to first crosses or 2-way crosses compared to purebreds, the effect of those 3-way crosses on average, 23% increase in performance. And so I say to, I think Jim Leachman used to say that something like getting heterosis in your herd is like having oil in your pickup. It just greases the whole system and it actually works better. The way I say it to my students is just get as much heterosis in your herd as you can. And what I'm trying to say there is don't just focus on getting a crossbred calf, but actually have as many of the cows with as much heterosis as possible and design a system that actually works for. So that's the base data. Yeah, sorry?
That green, how much of that is survival and how much is actually performance?
Yeah, some of it, there's definitely some for milk production, some survival of the calf, some pregnancy rate of the cow. There's lots of those different components, which is why it adds up to such a big number. I can't remember the exact number for how much of it's survival, but it is not all survival by a long way. It's partly survival, partly growth, partly milk production, partly pregnancy rate. It's all of those things.
Is that in that the three-way, is that second cross bull a different bull made with the breed?
Yes. Yes. So just imagine, for example, that the three breeds we've got are Angus, Hereford and Charolais, for example. So you might say, well, the best three-way cross would be an Angus by Hereford cow crossed to a Charolais bull or something like that. But this is actually would be the average of all of the three-way crosses. So if there were 6 two-way cross combinations, there are also 6 three-way cross combinations. So it's, let's to use that example. I'm getting a bit confusing in my own mind here, but you got one there where it's an Angus Hereford cross to a Charolais bull. Well, you could have another one that's a Hereford Charolais cross to an Angus bull, and all those combinations. So it is designed really, really well, and it is the average of all of those compared to the average of all of the two-way crosses compared to the average of the 3 pure breeds. And you could say, why would you do that? And the answer is to be able to understand the different genetic effects that go on. The best three-way cross was way better than that, and was better than the best purebred.
If you put a say first, the F1 was a Black Baldy, Hereford Angus. If you put a Black Baldy bull over Hereford Angus, do you lose all that breed?
That's a really good question. Daniel, could you hear that question? No. Yeah, sort of. I'll repeat it then. The question was, what if you cross a Black Baldy to a Black Baldy? That's sort of the fairly simple question. If you cross a Black Baldy to a Charolais, you'll get a full complement of heterosis in the calf because it's another different breed. If you cross a Black Baldy to a Black Baldy, that's actually an F1 by an F1, which what we call an F2. And in that, you lose half of the heterosis in the calf. It's still got a crossbred mum, so you've got 100% of the heterosis in the mum, you lose half the heterosis in the calf. Now, sorry? Yep, that's good example. One of the easy things to implement if you're trying to implement this sort of system is, buying. There's quite often Angus Simmental cross bulls around these days. Buying that sort of system where you got the growth and you got some heterosis and all that. So I think that's an easy way to implement that. One thing that I want to get to is that these things are all good and it's all theory, but now we've just got our handle so much better on actual selection within the breed that you actually are better off combining some of the heterosis, but also making sure you've actually got the ones with the highest breeding values in that as well. Pretty sure that's called composite breeding. Pretty sure there's people here who could supply composite bulls almost right behind you. Okay, I'll move on, but actually spending some time on this is really, really good because this is the foundation. From now on, we start to depart from the early work that was done well, and you could say, well, we no longer do good work. But I'm going to show you how we use genomics to be able to separate out some of the effects, how I believe we can separate those out. Yeah.
So after the third cross, how do you then, does it start to drop off then, and how do you bring it back to keep that heterosis
This is the problem in maintaining crossbred populations. Works beautifully in sheep where you've got a merino population that you can cross them to Border Leicesters. You're producing a superior F1 ewe, it moves in different geographical zone. And she can then be crossed to a Dorset sire or something like that. Structured program where the purebreds are ideal for one environment and then the crossbreds end up ideal for another environment. If you're trying to manage all 3 of those on the one farm, it gets complicated. But if you're only managing a couple of them on the one farm, it's not so hard. In a beef situation, if you start to get, you've got three-way crosses, and what always happens is people say, oh, gee, some of those heifers look nice. I don't really want to sell all of the heifers from that three-way cross. I'll keep some of them, but what do I mate them to? And if it was a Black Baldy cross to a Charolais, and then you've got these heifers that are big and lean and they look fantastic, but are they really the ones you want? It does become quite hard, which is why then either people throw away crossbreeding or they tend to go down the path of composite breeding, where you can get some of the advantages, not all of them, but some of the advantages, and get the advantages of selection at the same time, and be able to have a more marketable range of product, all those sorts of things. So that was a long answer, wasn't it? Sorry. All right, we'll move on, but I really do appreciate the questions and being able to lock that in. When I was doing my PhD, and I'll talk about this in another presentation later, I analysed some data in sheep, and I thought, well, is the same thing going on in cattle? So I actually then got in contact with some staff, Roger Barlow and Helen Hernshaw at New South Wales DPI at Grafton, and I said, I'm doing this work, but I'd really love to be able to test out some of my sheep ideas on some cattle data. Could I please use some of your data and analyse some of that? And sure enough, they were tremendous in letting me do that. So it wasn't actually Black Baldy data in, it was actually Brahman Hereford data in my PhD. And the thing that I actually found there was that they had done this great experiment. They didn't have all the fully designed crosses, but we were able to, they had enough crosses we could separate things out. And they'd raised them on 3 different pasture levels, low, medium and high quality pasture. And if you know the country around Grafton, you can find areas with low, medium and high quality pasture. And sure enough, in high quality pasture, when the breeds are more different, you tend to get more heterosis. Now, when on high quality pasture, sure enough, 20% growth, 21% heterosis for growth in Brahman Hereford crosses on high quality pasture. That's fantastic. But then when the quality of the pasture reduced, medium quality pasture it was only 13%, low quality pasture it was only 1%. So that then got me thinking, and this actually is what started me on a whole path of thinking about feed efficiency work, which I'll talk about in my other talk. But what I realised there was the heterosis effect cannot be improving efficiency of the animal. It must be increasing appetite. So that when the appetite is able to be met on the high quality pasture, when they were able to take in more energy, then the heterosis was able to be expressed, and you're seeing it. But if they were actually limited in their energy intake because of pasture quality, they weren't able to express the heterosis. So what that tells you is, and many people have said for many, many years that heterosis is the only free lunch that you get in cattle breeding, it actually doesn't come as a free lunch. It actually does cost something, in that I believe they actually are eating more. And sort of, it's a little bit like Durr, like you don't usually get something for nothing in biology. So that's what I believe is the mechanism, is that they actually are increasing intake. Now, if it's intake during spring when feed is cheap, that's fine. If it's intake during autumn when you're supplementary feeding during a drought, that's a total disaster. But they never perform negatively, and it's only when the opportunity was there that they expressed it. The other thing is that the heterosis for number of calves born in that trial was 39%. Huge. And you could say, well, not surprising with the Brahman and Hereford being more different, you get more heterosis, and Brahmans not having super high reproductive rates, but absolutely huge heterosis for reproductive rate. So that's affected some of my thinking that will come out in some of what we present. Now, presenting this stuff a little bit like Back to the Future, I think, and I think when I started working on this, I looked like Marty McFly. Pretty sure now I look a lot more like Doc. Anyway, let's move on. Now, what's some recent trials that have occurred? There's a couple of trials in the US that have occurred, and both of these have been comparing Black Baldies to pure Angus cattle. And there's not recent trials with really, really good designs. The multi-breed trial has a little bit of it, but there's not lots of recent trials to be able to review with really, really good design to be able to separate out those effects, because we've done it before and the results come out pretty repeatable. Anyway, in this trial at Circle A Ranch, Hereford side calves were 4.5 kilograms heavier. They were similar for fat depth. They had 5.9 kilogram heavier carcasses. They had slightly bigger eye muscle area, which is not bigger. They weren't more muscly. They were bigger, and so they had bigger eye muscles. So it's the same result as the growth result. Their average daily gain was 0.07 kilograms a day higher. That's converted from something like some 15th of a pound or something or other that they reported. And the heifer calves were worth $110 more. So there was a real advantage of the Black Baldies over the Angus in their system that they reported. There's a similar trial run at Harris Ranch where there was a slight advantage in pre-weaning growth. The morbidity was similar with a possible slight advantage for the crossbred, so that means it was slightly higher but not significantly higher. Feedlot profitability was $30 greater due to better feed conversion. The quality grade, so that's marbling, it's indicating marbling primarily, consistently favoured the Angus, and that was $15. These are not today's prices, $15.60 better. And the pregnancy rate of heifers improved by 7% in relatively short breeding season, and the difference was 93% for the Black Baldies versus 86% for the pure Angus. So it's sort of the results you expect. So they're the sort of trials that we're seeing in more recent times and typical advantages of Black Baldy over pure Angus. So the trial that we ran, we had 30 Angus size and 30 Hereford size. Most of the size that we used were AI size that were, AI size that were also used in Angus sire benchmarking or Hereford beef information nucleus herds or programs, so that we had genetic links to those programs. The other thing is that many of those sires were also used in the Trans-Tasman work in New Zealand, so that we've actually got formal links, but genetic links between a whole lot of research trials around the country. There are about 1,500 calves, so 743 steers slaughtered. The females were retained in the herd, and both the Angus and the Hereford sires have breed plan EBVs. Now, I had a question in here. Yeah.
Just on that last slide, and you might cover it later, but the feedlot profitability with improved feed conversion, is that, can you have both that and increased appetite, or are they?
Yeah, they had an increased appetite. They ate more and they grew faster because they were eating more. It is that simple. And animals that grow faster in the feedlot, if they grow faster in the feedlot, you're effectively diluting your maintenance, and so they'll have better feed conversion. Almost causal relationship. Good question. And so just to cut to the chase in terms of what the results were, the trial was run on a big farm in north eastern Tasmania that's actually a wind farm, and they leased the farm there. Hereford side calves were heavier at birth, heavier at weaning, heavier at slaughter, but had lower intramuscular fat. Does that sound like a very familiar result based on what the other trials showed? Absolutely, exactly the same result. A greater proportion of Hereford side calves were pubertal at joining and went on to wean 2 calves from 2 opportunities. So the Black Baldies had an advantage. The Black Baldy heifers were in slightly bigger, slightly better condition, and because of that, more of them had reached puberty, more of them got in calf. They then went on and raised more calves. Not huge differences, but there were more. The Hereford side calves born to heifers had increased calving difficulty and loss. Now, let me just drill down on this and think through what is a risk factor here. Now, it didn't happen in mature cows, it only happened with heifers. So the first risk factor is we're mating heifers. The second one is most of you would know that Herefords tend to have bigger calves than Angus. Would that be a fair call? Right, so the second risk factor is Hereford. The third risk factor is most of you would know that male-born calves are heavier than female-born calves. Does that sound fair? So when we had the combination of heifers, and they were stocked heavily, so those heifers were not overgrown, heifers with Hereford calves, Hereford cross calves at foot and the male calves, then you got more losses. Now, in the mature cows, the difference was absolutely zero. So it's really important to drill down. It's actually one of these times, and like Matt will know what I'm saying here, that very rarely is it worth looking at like a 3-way interaction in an analysis. But this is one of those times where it actually works, because the real issue was only male Hereford cross calves when they were born to heifers. Anyway, move on. Just in terms of some actual data to sort of show you how things work now, bigger carcasses have bigger eye muscles. So on the left-hand side, I've got on the vertical axis eye muscle area. On the horizontal axis, I've got carcass weight. The red dots are the Hereford side calves. They're not Herefords, they're Black Baldies. The black dots are purebred Angus. And can you see that in general, the red dots tend to be slightly to the top right a bit more, a bit heavier, and have a little bit more muscle, which is associated with growth. They weren't more muscly, they were just slightly bigger eye muscles because they were bigger animals. But there's a huge range there. So it tells you a few things. Yes, there's a bit of advantage, but focus on buying good animals within the breed as well. With the intramuscular fat, the graph on the right, same horizontal axis, carcass weight. So there's a full disclosure about all the carcass weights here. On the vertical axis, intramuscular fat, and that's chemically extracted intramuscular fat in the lab. And the highest intramuscular fat carcass was a Black Baldy. You wouldn't expect that, but it was. But on average, the red dots tend to be lower for marbling than the black dots. No great surprises. Things absolutely matched expectation. So because we expected that they would match expectation, we tried to build in a bit more measurement into the trial. And so we measured puberty in heifers and we did the genomics work. And I just want to report on some of that now. When we do the genomics, we can start to, we can separate out the relationships between the animals, and we can put them on these scatter plots and show how are all these animals related to each other based on the genomic information. Now, you can do that with pedigrees, but genomics just allows you to do it so much better. On the far right, in triangles, we have red triangles are the pure Hereford bulls that were used in the trial, the ones that were actually genotyped. We didn't get every single one. The left-hand side black triangles are the Angus bulls. Now, the Angus, purebred Angus calves from Angus cows, they are the bulk of the black circles on the left-hand side. Now, the Angus herd where we were trialling this, they actually had heard about Black Baldies before, because it actually isn't a secret. And so they had actually used some Hereford bulls before. So some of their Angus cows actually had some Hereford genes in them. And this pulls that out exactly. So those, if you go from the far left to across one blob, that blob of animals there are Angus side calves mated to supposedly Angus cows, but they turned out they were actually Black Baldy cows. Some of them first cross, some of them 3/4 Angus, 1/4 Hereford. And see straight away the genomics is picking up the fact that those calves had some Hereford genes in them. In that, on the right-hand side, you've got Hereford genes, and on the left-hand side, you've got Angus genes. Can you see what I'm talking about? And then the Black Baldy calves, you expect them to be in between the Hereford bulls and the Angus bulls. And sure enough, the middle blobs are the Black Baldy calves. And because some of their mums also had some Hereford genes, that actually means some of those Black Baldy calves actually were 3/4 Hereford, 1/4 Angus. And so the blob second in from the right, that's what that's representing there. So can you see how the genomics straight away has been able to pick up the relationships between these? We didn't have any pedigree on the cows. We didn't genotype the cows. We could tell some cows had white faces. That's as much information as we had on the cows, apart from the age, like we knew what year they were born and all that sort of thing. So there's some variation there. What the animals are down further and why those Angus actually, which bull that is right down the bottom left and why those, probably it's his calves there that are further down. I actually am not sure which bull that is or what is driving that. But clearly there's some variation in the Angus that's separating out on that other axis. But I reckon that's pretty interesting and shows how the genomics is able to separate out those different relationships. And what Steve talked about last night is the genomics, he talked about the length of the code and the information that's there. But really, the easiest way to think about genomics in my mind, and by the way, that was a tremendous illustration, Steve, I really appreciated it. But the simplest way in my mind to think about genomics is more accurate pedigree. That's as simple as that. I got 3 sons. They all had the same mum and dad, and it's pretty obvious from some of their characteristics that really is true. There's no question on parentage, I don't think. One's 6'6", one's 6'2", and one's 6 foot. Like, there's a fairly big segregation for height in my 3 sons. And now, if we were able to genotype them and show what genes they had inherited from their grandparents, then we'd be able to track that a lot better than just saying, on average, that they've got half of Wayne's genes and half of Jude's genes. And so what genomics would give us in that example is a more accurate pedigree. Now, here's just a tiny bit of theory to show what I'm going to allude to in a moment. What I've got here is representing 2 different breeds with only 4 different SNPs, as Steve alluded to them last night. The breed on the left, so it's homozygous for big A, which homozygous means that it's got 2 big A's, like there's no variation, as opposed to heterozygous, which means hetero means different. It's homozygous for little b, it's heterozygous for C, so it's got some variation within the breed for the C locus, so there's a big C and a little c, and for D, it's homozygous there. So the 2 breeds, if you compare the breed B, it's little a, so it's different to breed A at that locus, or that location. At the B location in the genome, it is different again. But one of them has, let's say, the favourable form of A, the other one has the favourable form of B. And then you get to the C, both of them have the same variation. They both vary in that C location. And then when you get to the D location, they both happen to be the same. This is very, very common to represent different types of things that can occur between breeds. And if we just got an average heterozygosity, in other words, we said what proportion of the genes or the locations in each of those breeds is heterozygous, both of them would be 25%, in that both of them have 1/4 of the genes that we've reported that are heterozygous. Can you see that? Okay, what we're going to do now is we're going to cross these 2 breeds. And when you do that, if you cross a big A to a little a, you end up with a big A, little a. If you cross a little b to a big B, you end up with a big B, little b. So you actually end up with more heterozygosity in the crossbred than you do in the parent breeds. This is what heterosis is. Inbreeding is the opposite. You just end up with things more homozygous. Now, and then if you cross big C to big C, little c, you could end up with big C, little c, or little c. Sounds like I've done that before in a lecture, doesn't it? So that one varies. And then if you cross big D to big D, you get big D. So that crossbred is not 100% heterozygous, but it is more heterozygous than the parent breeds. That's the principle of what happens at the genetic level in crossbreeding. Now, we can then use that information to be able to pull apart, and the genomics to be able to pull apart the different effects. So the genotype data we had on these animals, we had 40,743 single nucleotide base changes. We call them SNPs, single nucleotide polymorphisms. Polymorphism means many, poly means many, morph means form, many forms. Those that actually varied at a significant rate, so that if they didn't vary, we didn't include them in analysis, so minor allele frequency greater than 1%. The Angus, on average, had 41% of those genes were heterozygous. The Hereford crosses had 44.6% of those heterozygous. In other words, there's lots and lots of the genes that we looked at, there's lots and lots of variation in both breeds. But on average, not surprisingly, the Black Baldies were higher in heterozygosity than the purebred Angus. So that difference in heterozygosity of 3.5%, I believe that represents the heterosis effect. And so by having that now, we can separate out, even though we didn't have all the different crosses, we can separate out the heterosis effect from the other effects that are actually in those crosses. When we do that, we can then look at the fact that we've got breed plan breeding values on the bulls that are used. And one of the criticisms of the trial was, well, you're going to show that Black Baldies are better than Angus if you use all below average Angus bulls and all above average Hereford bulls. That sounds fair, doesn't it? Do you think the Hereford breeders would design it that way? Absolutely. Well, Not completely, because we genuinely used bulls across a range of herds that were used in their progeny testing programs in both breeds. There might have been a little bit of that, but not much. But we can adjust for that. We can actually pull that apart now. So if you look at, I've just got carcass weight circled there. The average EBV for the Hereford bulls being used for carcass weight was 63.8. The average EBV for the Angus bulls used in the trial was 63.4. But the Hereford bulls, they were... I'm just wondering whether that's... 51's the average. They were average. The Angus ones were above average. Does that sound right? It's the other way around. That's right. The Hereford ones were better on average than what the Angus ones were. That's right. Thank you. So we can then account for that. We can pull that apart. Just got my mind twisted there. Now, we can say for a whole range of traits that we looked at, with genomics, we can actually say, well, comparing the Black Baldy to the purebred Angus, how much of the effect was the heterosis effect versus how much of it was the Hereford effect? And we can separate that out now. So for calving ease, the heterosis actually improved, the blue lines are heterosis. The heterosis improved calving ease. The Hereford effect detracted from calving ease. Remember that the calving ease of the Hereford really was only male cross calves mated to heifers. So if it only made to mature cows, it was not a problem. Birth weight, a little bit of extra birth weight from heterosis. What do we got there? 2%, 5.5% extra from the Hereford genes. With weaning weight, heterosis increased weaning weight. Actually, Hereford added nothing in that respect. And in fact, on carcass weight, the Hereford genes were actually below the Angus genes, whereas the heterosis effect overcompensated for that. So the crossbreds had more carcass weight, but that actually was due to heterosis, not due to the Hereford genes. And the Hereford genes actually were a slight negative in that respect. Eye muscle area reflects that carcass weight result. The fat depth, the heterosis effect increased fat depth, increased their appetite, they ate more, they got fatter. So it matches with our old data. The rib fat one was a bit interesting, and maybe because there wasn't much variation, we ended up with big percentage differences there. Maybe that's even the case for the P8. For intramuscular fat, that's an actual value, not a percent of a percent. And the heterosis effect for intramuscular fat was 0, exactly what was reported in other trials. And not surprisingly, the Herefords had 1% less intramuscular fat than the Angus cross calves. If the carcasses had been grown to a higher weight, higher condition, then the difference would be even bigger, I believe. Now, because the Hereford bulls had breeding values on them and the Angus bulls had breeding values on them, and we estimated their breeding values in our trial, and we were able to estimate those separate from the heterosis effects, so lock that in, we've actually got breeding values in our trial, breeding values from breed plan, and the average breeding value of a team of bulls is a very accurate measure. And you all know that bulls' breeding values can change over time, but the average breeding value of a team is a very accurate value. So we've got very accurate values of breeding values of a team of 30 bulls from breed plan. We have very accurate values in our trial of bulls, of 30 bulls in our trial. Now, because we've got both of those accurate values, we can adjust the values in the trial to the values in breed plan, or vice versa. We can adjust the breed plan values to our trial. So we can actually produce multi-breed EBVs from a trial with Black Baldies. And when we do that, we then actually report the percentile bands. So this is now, I believe, the two breeds being compared, absolute apples with apples, heterosis effects removed. What are the percentiles of each of the breed for trait? And what I've got reported here is what is the breed average Angus if it was reported on a Hereford breed plan base. Now, the red bars are the Hereford reported on on the Hereford base, which means by definition the Hereford ones are all 50% because 50% is average. the 50 percentile. Now, for calving ease, the Angus ones are exactly on the 50 percentile if they were reported on a Hereford breed plan. For birth weight, Angus would be, and now remember we want low birth weight, so the Angus are at the 95 percentile. So a breed average Angus is equivalent to a top 5% Hereford. Do you understand the way the data's going? For weaning weight, a breed average Angus is equivalent to a top 40% Hereford or a 60 percentile Hereford. For carcass weight, a breed average Angus is equivalent to a top 5% Hereford. That's a big challenge to the Hereford breed. Eye muscle area reflects exactly the same as carcass weight. The fat depth ones, pretty much it's saying they're the same for fat depth. And intramuscular fat, a breed average Angus, bearing in mind that out in the pens we have some above breed average Angus, but a breed average Angus is equivalent to like a top 1% Hereford. That's how far Herefords are behind Angus for intramuscular fat. So I believe that we've got multi-breed EBVs that are, and breed comparisons that we can pull out of this trial.
Wade, how representative of their respective breeds do you think those 30 sires were for each breed that you had?
Yeah, so the question is, how representative do I believe those sires were for the breeds? There's a lot of variation in them. I think pretty good. Both the sire benchmarking and the Hereford bins. I mean, Andrew's here and was involved in some of the... Where are you, Andrew? Andrew was involved in choosing some of those in the later part of the trial. I reckon pretty good. You're not going to be choosing like bottom 10%, but pretty good for where both breeds are going. Fair call, Andrew? Yep. Now, I actually misquote Johnny.
Along the same vein as that, what was the accuracy of the EBVs?
Yeah, so the question was about the accuracy EBVs. Now, all of the bulls had progeny in breed plan, so they're reasonably accurate. All of the bulls had progeny in ours, so they're reasonably accurate. However, the accuracy of the average of a team of bulls is extremely accurate. And that's the principle that we're using here. We just did a simple, what is the difference between the groups, not what is the difference between every single bull. Now, I actually misquoted myself in the yards yesterday, 1 centimetre. So now we're looking at what impact did breed plan breeding values have on what we actually saw in the field. 1 extra centimetre of scrotal circumference in the father's EBV related to 3% more of the heifers being pubertal going into mating. Yesterday I said 1%, I apologise for that. 3% more pubertal going to mating. 1 day shorter in days to calving EBV led to 1% more pubertal going into mating and 0.8% more calves weaned per cow joined. Now, I said 1 yesterday, but I knew I was rounding 0.8 up to 1 because 1 is a value that I've heard my AgBoo colleagues quote over many years as a really rough guideline. In young animals, it could be more. Averaged across the herd, that is a reasonable value, matches exactly expectation, and Matt's nodding vigorously to agree with that.
Brahmins, I think that one day increase in days to calving equals 1% improvement in calving weaning rate is a number that's come from Brahmins.
Averaged across mature cows as well as young heifers. So that's not a heifer value. That is, in heifers, the effect is likely to be bigger, I believe. In average across the herd, that's quite robust. That figure, lock it in. So those figures are fairly good. I just made a mistake on that 3% pubertal associated with the scrotal one. So I need to just give Herefords a bit of a plug for something that I've seen some data that shows a real positive. If you think about what Shane was talking about yesterday about the cost of getting calves on the ground, he had that nice table in the document around number of joinings versus cost of calf on the ground. And I heard a talk from Anthony, how do I say it, Andrew? Uren? Thank you. I don't know him well. I heard a talk from him and he buys bulls, I think, from here and from Warina, and he just reported what results they get in their commercial system. And this is a lot of data, 12 years data, 378 bulls. They join twice a year, so they're getting good value out of their bulls. They do bull breeding soundness examinations before every single joining. So there's 795 evaluations that they have. They had an annual failure rate of their bulls of about 20%, slightly higher, Shane. You said 15 to 17% bull replacement per year. The average number of joinings of the Angus bulls was 3.1 and the average number of joinings of the Hereford bulls was 5.4. That's a big difference. Now, Dinny said to me yesterday that the Angus bulls tend to be more aggressive when they're young, and this might reflect that. I don't know. I haven't done any research on this, but this is a very interesting result, I think. One of the things with the trait like this is that, just hang on one sec, Brian, breeders can't select to improve this because all of the phenotypic expression occurs in the commercial herds. Like even the bulls that breeders use is such a small number, they can't really select to improve this. So the only way we can improve this as an industry is to work with large herds, with large contemporary groups, and do genotyping them, so use genomic selection and use that in our genetic evaluation system. So this is a challenge for industry to get good data to be able to make ongoing improvement.